In this video, I just want to go through a couple examples of how to solve an exponential equation by getting common bases. So when you have an exponential equation, you could take the log of both sides, but in this scenario, it's going to get a little complicated using that method. Fortunately, we have a rule that says that if I have a base to the power of m equal to that same base to the power of n, then m equals n. We can use this property in this situation because we can rewrite 3 and 27 to have the same base. So think to yourself, how can I rewrite 3 and 27 to have the same base? What common base do they share? And hopefully, you thought of base 3. So on the left, it's already 3, so I can just leave it as is. On the right-hand side, 27, we have to think 3 to what power equals 27. So we know that 3 cubed equals 27. So notice that all I did was I replaced 27 with 3 cubed. And I can do that because 27 equals 3 cubed. You can't just replace 27 with any number. Like I can't just put 3 there. The goal is not necessarily to have the exact same number here and here. It's just to have the same base. So 3 equals 3. And here, 27 equals 3 cubed. So I didn't change the number. I just changed how it was written. And that's really important to understand. I see a lot of students just change the number. You can only change it to an equivalent form with a different base. Now that we've gotten that far, we can distribute our exponent here. So I get 3 to the power of 3x minus 6. And on the left-hand side, I still have that 3 to the x plus 1. Now I have the same base. So now I can use this property. Now I have the exponents equal to each other. And now I have just a linear equation to solve. I can subtract x on both sides. I can add 6 to the other side. Divide by 2, and x equals 7 halves. Don't forget to circle your answer. You can always test it back in to see if it makes the statement true. Make sure you substitute it in everywhere you see an x, and it has to make that statement true. Let's look at another example. We still want to use the property of b to the m equals b to the n so that we can set our exponents equal to each other. So we want to get that common base. So for this example, I'll call this example 2. Let's look at let's see, 3 to the 4x minus 1 equals 1/9 to the power of x plus 2. So again, I want to get the common basis. I can't just change the number completely. I can only rewrite it to have the common base. So if I look at 3 and 1/9, I know that students often have trouble with those fractional exponents or exponents that turn things into fractions. So just as a quick little review, remember that, we'll do this on the side, if we have a to the negative m, that means 1 over a to the positive m. So right now, I've got 9 in the denominator, and I know that 3 squared is 9. So right now, I have 1 over 3 squared. So I'm working with the fact that 1/9 is 1 over 3 squared. So what I want is I want that 3 in the numerator. So I can use the other side of this rule in the blue on the right that says 1 over a to the negative m equals a to the positive m. So that negative exponent moves it from the numerator to the denominator and vice versa. So if I want to move this 3 squared to the top, then I just have to make this 3 to the negative 2. So 1/9 is the same as 3 to the negative 2. So I can replace 1/9 with 3 to the negative 2. Bring the rest of my equation down. Now I've got almost common bases. I want to work with this exponent, distribute that on the right. Make sure you distribute to both terms. Now I've got common bases. Now I can set the exponents equal to each other. And now it's a simple linear equation to solve. Divide by 6. And x equals negative 1/2. So for these next couple examples, you give it a try. So for example 3, I'm going to write the problem down. I suggest that you try it as well. And just pause the video, give it a try, and then you can watch the video to see if you are correct. So let's try 25 to the 2x minus 5 equals 125 to the x plus 3. So give that a try. Okay, let's see how it's done. I know that 25 and 125 can both be rewritten as something with a base of 5. So I can rewrite 25 as 5 squared because 5 squared is 25. I can also rewrite 125 as 5 cubed because 5 cubed is 125. So notice that I'm not changing the numbers here. I'm just rewriting it with a different base. Now I can distribute my exponents. So 5 to the 4x minus 10 equals 5 to the 3x plus 9. Now I've got common bases. Now I can set the exponents equal to each other. And now I've got a linear equation to solve. Subtract 3x from both sides, add 10 to both sides, and x equals 19. Here's one more for you to try. This one has a fraction, so let's give that a go. Let's say we have 1 over 16 to the x minus 5 equals 64 to the 2x. So I know that 16 and 64, well, actually you give that a try. Pause it, give it a try, and then play the video. Okay, we know that 16 and 64 can be written with a common base of 4. So 64 I know is 4 cubed. Now the 1 over 16 sometimes causes some trouble. So I know off to the side, I know 1 over 16 is the same as 1 over 4 squared. And so to get that to the numerator, I've got to make that 2 negative. So this becomes 4 to the negative 2 to the x minus 5. Can distribute. Distribute here. Now I've got common bases, so I can set those exponents equal to each other. Add 2x to both sides. Divide by 8. Careful here, sometimes students accidentally divide by 10, but remember we want to get rid of that 8 where the x is. So x equals 10 over 8, which is 5 over 4. And you're done. So hopefully you have a little better understanding of how to solve these equations by getting the same base. Just remember that you want to make sure that you replace it with the equivalent expression and not just some random number. Good luck.